Okay, in this video we're going to talk about, by the way, this is pre-algebra video, chapter 1, lesson 6. We're going to talk about scientific notation. Our objective as the student, I can use scientific notation to write large and small numbers because I want to be able to describe situations quickly and efficiently without having to say giant numbers. For example, look at the bottom of the screen. You see 2,850,000,000. Now, that could be a lot to write or even a lot to say. So as an example, we could write that with scientific notation as 2.85 times 10 to the ninth power. And that's also going to allow us to make it a lot easier for us to do computations with that scientific notation. It's something that scientists and people who work with very large or very small numbers use on a regular basis. Or, for example, let's say we had something very small, such as in the bottom right hand of our screen, 0.00034, otherwise known as 3400 thousandths. That's a bit of a mouthful to say, or you can write that in scientific notation as 3.4 times 10 to the negative 4 exponent. Now, I'll talk in a minute how we set that up in scientific notation, but I do want to point out just a brief thing you may already realize is you may have noticed, and this first example, 9 was positive. That means it's going to make our number, in this case 2.85, larger, because 10 to the ninth power, that's a lot of zeros that we're going to be adding, because remember, multiplying by 10 adds 1 zero, multiplying by 100 adds 2 zeros, and so on. So our number is going to get a lot bigger. But when we say adding zeros, what we're also technically talking about is we're technically talking about moving that decimal over, and in this case 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So decimal is going to go here, then all those blanks are going to get filled up with zeros, and that's where all these zeros came from. So what you see down here would be our scientific notation. This could be the standard form of it, the actual just regular old number is what those could be. Now, on the example on the right, with it being a negative exponent, that means our number is going to get smaller. Our 3.4 is going to get smaller. And because it's getting smaller, we're going to move that decimal to the left 4 spaces. Now, I'm going to go ahead and delete that because it's going over into the other side. But that way it's going to make it small, and those empty spaces are going to get filled up with all of those zeros. So it's going to be a very small number. But now we're going to go more in depth of doing some more examples with doing that. So sometimes people like to see these descriptions with symbols so that makes sense to them. So for example, if you had the format of some number times 10 to the n power. For scientific notation, a, that some number, has to be somewhere between 1 and 10. It can be 1, but it cannot be 10. It needs to be one digit, in other words. At least one digit in front of the decimal. So it could be 9.9999, or it can be 1. 1's the smallest that it can be. So it must be something between 1 and essentially all the way up to 10. And then n, the exponent, right here, n is just going to be some integer. It can be positive, it can be negative, like the quick review I just showed you on the first screen. So as an example, let's say we had 425 million, and your instructions were to write this into scientific notation. Well, first you want to confirm that you know where is the decimal currently. If you don't see a decimal place, that means it's at the end. So that means we just need to figure out how many times do we have to move this so that we have one digit in front of the decimal. That's essentially what we're going to do. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. We would have to move it 8 times. So that means, as scientific notation, we have 4.25, since that decimal is between the 4 and the 2, times 10. Now, in order for our decimal right here, our 4.25, to get bigger, back into 425 million, it's got to get bigger. So for that reason, the exponent on the 10 has got to be positive. Let me erase that. It's got to be positive because we've got to be able to make it get much larger. Now, if we were saying, let's say the one we wrote here was already a big, like 1 or more, we want to make it smaller, we would have a negative exponent on. Let's say, for example, we're talking about the total human height. Let's say we took the approximate 7 billion humans on the planet Earth, and they all stood on top of each other's heads. Now, assuming they didn't crush the people at the bottom, we would have approximately, according to the statistics, about 10 million kilometers. But that's sometimes a large number, especially if we're going to talk about computing it or working with it. So what we can do is we can change that to scientific notation, where the decimal is currently on the end, so let's count how many times we have to move it. 1, 2, 3, 4, 5, 6, 7. Remember, you have to move it to where you only have one digit to the left side of the decimal. So 1.0, or in this case we just leave it as 1 since there's nothing after the decimal, times 10, and we counted 7 times. 1, 2, 3, 4, 5, 6, 7, yes. So that would be the scientific notation, kilometers, so that we would know, be able to work with it maybe for calculations. That way it's another example of expressing a very large number with scientific notation. Now, in this next example at the bottom, the width of human hair is given, if it was given to you in scientific notation, 1 times 10 to the negative 4 power, but your job was to find out how much was that in actual standard form, in actual numbers, maybe gives you a better idea. We're going to start off with 1. Now it's 10 to the negative 4, so here we're actually converting it from standard notation into its regular form. So that means it needs to get smaller. That one, it makes sense. That does make sense because human hair is very, very small. So 1, 2, 3, 4. Now you'll notice these blanks are going to get filled with zeros. So that means 0.0001 meters. That's how wide a human hair is. And as a thought, by the way, that's about 100 micrometers for what it's worth. Now, in this example, we're told that the distance from the Earth to the Sun is in scientific form, scientific notation, is 1.5 times 10 to the 11th power meters. Now, if we want to know maybe more realistic, what would that number actually be, we can convert it. So if it's 1.5 times 10 to the 11th power, that means we have to move the decimal over 11 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's see how many zeros that's going to be. Fill all those spaces in. We already know since we moved it over once to get on the other side of the 5, we're going to end up having 10 spaces. So you can kind of predict that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly, 10 spaces. So that tells us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Throw in some commas every 3. There we go. Alright, so thousands, millions, billions. So that's 150 billion meters is what that's telling us. But obviously it's not very reasonable to measure that distance in meters, even though that is the answer to this question. But for those that are curious, it would be more appropriate if we're in scientific terms. We would use kilometers, and there's 1,000 kilometers, 1,000 meters in every kilometer, so we would just chop off 3 of those zeros if we want to know how many kilometers it was. So 150 million kilometers. Alright, so I'm essentially just going to leave you with a few more examples I want you to try. Press pause, make sure you knock them out on your own, and press play and see how you did. At that point, we're all done. Alright, so these are the ones I want you to give a shot. The top 2 you're going to write into standard form since they're currently in scientific notation. The bottom 2 are already in standard form. I want you to write them into scientific notation. Press pause, give these a shot, and then see how you did. Now for the first one, you'll notice it's times 10 to the negative 4 power. That means we're getting smaller, which essentially means we're dividing by 10, dividing by 10, dividing by 10, dividing by 10. Or you could just simply say dividing by 10,000. So okay, so anyways, so for the first one you're good. Make sure you have 3 zeros in between the decimal and the 8. Now for the second one, times 10 to the 3rd power, that means we're getting bigger. So we're going to move that decimal 3 times. Since we're getting bigger, it's to the right. So now the decimal is going to be here. We fill that in open space with a 0. That tells us 2080, 2080. That's that one. Give the second to a shot. Give the second to a shot if you have not done so already. Alright, for these last ones, for the 52,300,000, we got to move it 7 times to make it 1 digit in front of the decimal. So we have 5.23. And so, but since our new our new scientific notation version, it needs to get a lot bigger. That's why it's times 10 to the positive 7 power, because it's got to get a lot bigger. In order to get bigger, it's got to be a positive exponent, or it's got to essentially move the decimal to the right to get bigger. Now for the one on the bottom right, our last example, our scientific notation number is 8.46, but our original number was really small, something between 0 and 1. So it means we needed to get a lot smaller, and we counted it was 3 spaces it needed to move. Since it needs to get smaller by 3 spaces, this times 10 to the negative 3 power. Alright, so we did a bunch of examples of scientific notation. We also kind of gave you some ruled examples of where it can be used, such as distances in the solar system, really small things like the width of a hair, or a cell or an atom, things like that. These types of things, when people are describing them, maybe you're somebody who looks out into the night sky, or maybe you're somebody who's into biology. These are the types of measurements that can be used to describe very small or large items. That's why we like scientific notation.